Good evening. I'm John Grant. I'm the chairman of the Center for Earth and Planetary Studies here at the National Air and Space Museum, and it's my pleasure tonight to welcome you to the first in the 2010 Exploring Space lecture series. Tonight we'll be hearing from Rosaly Lopes about where the hot stuff is, volcanoes of the Earth and solar system. But first, I want to mention that the Exploring Space lecture series is generously supported by Aerojet and NASA. And I'd like to take a second to personally thank John Schumacher of Aerojet, who is here this evening, and also Lika Guhathakurta and Mike Kelly, who are here from NASA. Thank you for your support. Okay, Dr. Rosaly Lopes was born in Brazil and moved to England in 1975 to study astronomy. Many of you have heard a lot of this because I was standing downstairs listening to the Q of A at the University of London. She graduated with honors in 1978 and stayed on to complete her PhD in planetary sciences in 1986. Her thesis was on comparing volcanic processes on the Earth and Mars. And after that, she began a career at the Old Royal Observatory in Greenwich, and in 1989 performed hazard mapping at the Vesuvius Observatory in Italy, which I heard was the first volcano that you studied. She's now a senior research scientist and lead scientist for geophysics and planetary sciences at JPL. She began there in 1989 as a National Research Council resident research associate. She became a member of the Galileo Flight Project, soon thereafter working on the near-infrared mapping spectrometer, or as many of you may know from the many NASA acronyms, NIMS. That team and those data that she collected led to her discovery of 71 volcanoes on Io that had previously not been recognized. In 2002, Rosaly joined the Cassini radar team, and she uses those data to show that Saturn's moon Titan has volcanic features that are probably related to ice volcanism. She served on numerous NASA and National Academies committees and groups, and has awards that include the 2007 NASA Exceptional Service Medal, the 2005 Carl Sagan Medal from the American Astronomical Society. She's written numerous papers, articles, and books that include a couple that are on sale here tonight. The Volcanic Worlds, Exploring the Solar System's Volcanoes, the Volcano Adventure Guide, and Alien Volcanoes. She's been featured in numerous documentaries. She's a strong supporter of education, diversity, and outreach, and her hobbies include scuba diving, hiking, and no surprise, traveling to and collecting art on volcanoes. Please welcome and join me in welcoming Rosaly Lopes. And before I forget, and while she's walking up, please be sure and turn off your cell phones and pagers so that we cannot be interrupted while she's speaking. Thank you very much. Rosaly.
Thank you, John. Thank you so much for that introduction. That was a nice Q&A. I never had one of those before. Also, I have never lectured before in an IMAX theater, so this is really a new experience for me. I'm sorry I don't have any 3D stuff. So we find volcanoes in a lot of places in the solar system. Mercury, Venus, Earth, the Moon, Mars, and some moons of the outer solar system. So here is just a sketch, but with real images of the planets. Now, I used to have Pluto, but, I'm taking it out. It's good to have Photoshop. And this is a volcanic cone in Hawaii, on Kilauea. And this is what we call a fire fountain, which is one of the most beautiful things you can see on volcanoes. It's just when lava is spurting out, and it's coming out really like a fountain. So we'll get into that a little bit more later. But where are volcanoes on Earth? Well, probably most of you know about plate tectonics. This is a drawing made by Michael Caro. I'll show several illustrations by him. He's a space artist. And so the Earth has these tectonic plates, and volcanoes happen mostly at plate boundaries, either where plates are spreading apart or when they're colliding. So we see here that California is an exciting place. We don't have much in terms of active volcanoes these days, but we have a lot of earthquakes. And so here is another drawing showing the plate boundaries in blue, the earthquake zones in yellow, and the major active volcanoes in red. The Earth has around 600 volcanoes considered active on land, but most of the Earth's volcanoes that are active are in fact under the ocean, such as here on the mid-Atlantic ridge. And you get islands poking up, like Iceland. Very active place, great place to visit in the summer. But we also find some volcanoes in the middle of plates, such as Hawaii, and that is a hot spot, and I'll talk more about that later. So most of the Earth's volcanoes are under the ocean, and this is an image taken from a submersible in the East Pacific Rise. And in fact, the fellow who took this image used to work for National Geographic, and he told me some of the story about when they were really puzzled, scientists were really puzzled about what was happening under the ocean. For example, one oceanographer showed him some of her images, and she said, something is happening to the camera, I just see like black. And he examined the images and said, no, actually, there are points of light. What's happening? There's nothing wrong with the camera. You're photographing something very dark. And these were from remote cameras before they really discovered these black smokers. When volcanoes erupt and break the surface, we have eruptions like Surtsey, an island off the coast of Iceland. And that happened in 1963. That photo was taken, in fact, by my PhD advisor. And you get a lot of explosive activity as hot magma comes in contact with water. And again, very wonderful to observe. There are many different types of volcanic activity, and we classify them and give names to them. And the important thing is that these are different types that usually mean different compositions, and the volcanoes that they form look different. The activity is very different. And when we're studying volcanoes on other planets, one thing that we often can't get are samples. You're studying volcanoes on Earth, well, first thing you do is go there and with your rock hammer and collect some samples, but it's actually very expensive to do that with spacecraft. So we use remote spectrometers, but also images, and we try to relate shape morphology to composition. So understanding the types of activity is very important, is also important if you want to go visit volcanoes on Earth, because there are some that you can visit very easily and be right there by the activity, and others that you should really get out of there if they start erupting. So this is a lava lake, is about 100 meters across, I think in Itoali, Ethiopia, and it's a place I haven't been to, but it's pretty much on top of my list, and this is taken at night. So lava lakes are wonderful to see because you can stand right on the edge of them and just see this lava moving around. And as we'll see later, there are a lot of lava lakes on Io. Geothermal activity is what you get in Yellowstone. Hawaiian and Icelandic activity are the mild eruptions with lava lakes, fire fountains. Strombolian is where you get mild explosions, such as this one is a cone on Mount Etna. And then you start getting the nastier types, the more and more explosive. Palaean, Vulcanian, this is also Mount Etna, but it's a Vulcanian eruption. And you see people here in the foreground. They are actually volcanologists, friends of mine, and they got out of there pretty quickly. And then Plinian and ultra-Plinian, which are the most explosive and most dangerous types. Now, most of these are named after the places where they typically occur, such as Hawaii, Iceland, Stromboli, and Volcano in Italy. Palaean is named after Mont Pelee in Martinique. Plinian and its more violent cousin Ultra Plinian, actually named after a person. He was a Roman general called Pliny the Elder. And when Vesuvius erupted in 79 AD, he was called to try to rescue people. And he died while trying to rescue people. And his nephew was known as Pliny the Younger, had been well-trained in philosophy, natural sciences at that time, and he described the eruption very well, observing it from a distance in a letter to a Roman historian called Tacitus. And that's what we consider the first scientific description of a volcanic eruption, so that's why this is named after both of them. So, we just want to show a few places that are more or less near Washington, D.C. I know that a lot of people here go on vacation to the Caribbean. And so we have Mont Pelee in Martinique that is quiet at the moment, and also Soufriere in Guadeloupe. But these are volcanoes that are capable of very nasty explosions. And Soufriere Hills in Montserrat that has been erupting for a very long time. And the island of Montserrat went from a beautiful place to visit. It was known as the Ireland of the Caribbean, all green, and now it's very gray. So what causes some volcanoes to be really explosive and other volcanoes to just erupt gently? It's mostly the type of rock. When magma is deep within the earth, it's at high pressure, there are gases dissolved in the magma. And as the magma moves up and the pressure becomes less, these gases want to come out. So it's a bit like opening a bottle of soda. And if the lava is very fluid, the gases can bubble out quickly. For example, in Hawaii. And if the lava is very sticky, the pressure becomes greater and greater and greater until it finally just explodes, and that lava just gets blown up to ashes. It also, of course, depends on the amount of gas that the lava has. You can have some lavas that are very sticky, but they have very little gas content, so they just kind of ooze out. But, basically that's what makes volcanoes different. So if you know what kind of composition a volcano mostly is or mostly erupt, and you look at the history of the volcano, you can pretty much predict what type of eruption it's going to have. So you know if it's a volcano dangerous to visit or not so dangerous. And the tricky thing is predicting when it's going to erupt. So Kilauea in Hawaii has been a wonderful place to visit for quite a long time now. It this latest eruption started in the early 80s. And it's had a lava pond, it's had fire fountains. You can go to Hawaii and you almost always can see something. You can see lava entering the ocean. You can, if you're energetic, you can hike over the lava and watch the plume as the lava goes into the ocean. You can take a boat out in the ocean and see the lava coming down. So it's a very wonderful place to visit for anyone who is interested in volcanoes. Strombolian, well, those are the mild to moderate explosions, and they form cones. The Hawaiian volcanoes tend to form shields like Mauna Loa. They're called shields because the name came from Iceland. They look like warrior shields on the ground. And one very nice example of a past Strombolian activity in the US is Sunset Crater that erupted between 1064 and 1250. That's in Arizona. So those of you who visit Arizona, you can visit Sunset Crater and see the cones there, and very educational, very nice. And you can see Strombolian activity on places like Mount Etna. In fact, that's very common there. So we would actually try to collect fresh samples from this kind of Strombolian activity, And the trick here is that you have to watch it for a while and see how far the bombs are landing. And then you try to stay out of range of the bombs unless you actually want to go and collect the sample. So what you do is you actually look up, and if what we call them bombs, these big chunks, they don't explode, but they just come at you. And so you look up and you just kind of dodge them. And you know, it sounds harder than it is. And one thing not to do is you don't run, because if you run, you can't see what's going on. If you turn your back on it and run, you can't see what's going on. Unless the density of bombs is so high that you know they're going to get you, in which case, well, bets are off. And so my PhD advisor and the most senior volcanologist really, you know, trained me very well on this, and I went in range several times to collect samples and so on. You know, and then one day we go, a new eruption starts, and we go there, and the eruption stopped. When we got there, that was 1981 on Etna. And so two of us walked to the cone, you know, me and the professor. And then we start hearing a noise, which is almost like glass against glass. And that's the noise that lava flows make when they move. And so he told me, oh, this thing's not dead yet. And if something happens, you know, go that way. And so, okay. And don't put your backpack down. So he just finished saying this when the thing exploded. And he looked up at the bombs and he said, run. You know, and I thought, he always told me not to run. But, you know, then, well, old guy was running, you know, what was I going to do? So I ran as well. And then I said, what's this? You always told me not to run. And he said he had judged the trajectory of the bombs and figured that we could get out of range before they landed. But you have to be very experienced to be able to do that. So that was exciting. Well, of course, the name Stromboli comes from Stromboli, which is one of the Aeolian islands off the coast of Sicily. And it's a wonderful place to visit, wonderful volcano that was made very famous in this movie in the 1950s called Stromboli with Ingrid Bergman. And that became kind of infamous because it was during that movie that Ingrid Bergman and Roberto Rossellini started their affair. And the poster for the movie actually said Raging Island, Raging Passions, and I just love it. And these days, you can go walk up to the crater, see from a vantage point, there's a group I was with, the explosions in the crater at night is really nice, or actually at dusk is the best time to photograph volcanoes. So that's a pretty easy place to visit and very nice. People used to like to camp up there and actually sleep. I think that if you're near an active volcano, if you're on an active volcano and actually near the range of bombs, you shouldn't go to sleep. And in fact, someone got hurt when a bomb came over their tent. But still a great place to visit. Another great place is Yazur volcano in Tana Island in Vanuatu. Vanuatu became known out here as one of the places in the Survivor series. And in fact, I actually saw the place where they filmed it, which is a point of land right across from a major resort. They weren't really in that much danger. And it was on another island. It didn't even have an active volcano. It's a very nice volcano. You can drive almost all the way to the top, and just a short hike, you get to look down on the crater, and it's wonderful. And this is one of the few pictures I have of me with my back to the volcano. And the man who took that was a professional photographer, you know, and he said, you know, one problem I found with your book is that there are no pictures of you on a volcano. And I'm usually too busy to photograph myself. And, so he took all these pictures, and until it had a more violent explosion, and I actually felt the shock wave on my back. Then I jumped up and I said, "Look out." And sure enough, a bomb came over the rim, and it was actually pretty big, about this size. And it landed about 30 feet away from us. And it was actually very welcome because even though it's a tropical place, it was getting quite chilly at night, but that warm bomb actually was great. And lava cools quite quickly, so it formed a cooled crust, but it was, still pretty hard to detach. And so we all huddled around this rock, and this Australian guy came by, and he was very puzzled, why are you all around this rock? It's warm. So they can be very useful. So Mount Etna in Sicily has some dangerous eruptions too. This is volcanic activity on Mount Etna. And on my second field season on Etna, in the first one, there was this great Strombolian activity, which was almost fire fountaining. It was just beautiful. But the second time I went, just a few months later, actually Etna had an explosion that was not very violent by volcanic standards, but they used to take tourists up to the crater, and the explosion was very unexpected, and it killed several tourists, unfortunately. And that's because, again, they just ran, and they didn't look to see where the bombs were landing. And we were about a mile away from that and helped rescue some people and drive them down. But that was a good lesson that, volcanoes are very beautiful and very exciting, but they can also be very deadly. And one of the most deadly eruptions in recent times was the one of Mont Pelee, Martinique in 1902. This eruption killed about 30,000 people, and it destroyed the town of Saint-Pierre, which used to be known as the Paris of the Caribbean. There were very few survivors. Most of them were at the edges of town. There was one guy right in the middle of the town who survived, and he was in prison. In fact, here is his prison cell. He was a black man called Siparis, who had assaulted a white man. So, in those days he was in big trouble. And he was in this almost totally underground cell, and he escaped the pyroclastic flow. Now, pyroclastic flow is the most deadly thing a volcano can put out, and that destroys everything in its path. And I'm going to show you a picture of a pyroclastic flow. But he was in a relatively safe place. He was burned badly, but he was rescued, and in fact, eventually he came to the U.S. and became a member of the Barnum and Bailey Circus and toured around. And this is so his cell, which you can still visit, and this is a picture at the time of the eruption in 1902, just showing some of the devastation. And this is the crater these days, so you can hike up to the top, and nothing much is happening there at the moment. But where we're still having a lot of pyroclastic flows is in Montserrat, in Martinique. The eruption started in 1995, and we all thought, well, it might go on for a couple of years, but no one expected it to go on for as long as it has. And this is the island, and here's the volcano. So it started to have pyroclastic flows that really started devastating the island, and then ash started getting everywhere. So I was there in 1996, and it was very unpleasant because even in the north end of the island, which was safe, you still get this fine layer of ash everywhere. And this is one of the eruptions in August 1996. And here is a great picture of a pyroclastic flow. So pyroclastic flows happen when you have a big volcanic explosion, and all this material, these ashes and small particles go up in a column of hot gas, but the column is so dense that it essentially collapses, and that flow of gas and ash and cinders, if you like, it can flow at hundreds of miles an hour. It destroys everything in its path. It can flow uphill. It's got so much energy. So you can't escape from one. And this shows that the lighter parts of the pyroclastic flow even can flow over water. So unless you have scuba gear, you can't even survive by going in the ocean. And so that was a very interesting experience for me, because I normally study the basaltic volcanoes, which are the mild types like Hawaiian, and Etna can be violent, but most of the time it's okay. And I went to Montserrat, and here is the Tar River valleys, where a lot of these pyroclastic flows are coming down. And so when we went to collect samples and do field work in this river valley, we actually had this practice of parking the cars on the road facing away from the volcano with the keys in the ignition. And that's telling you something. You might have to get out of there in a real hurry. And one day, this is a beach, sorry, cut off a little bit, it's formed in 1996. New beach formed by the pyroclastic flow. The sand is not nice. It's not going to become a tourist destination. It's all ash. And we came here by helicopter. We were dropped on this beach by helicopter, and the first thing I did was to look around for a place to hide if a pyroclastic flow came down, because it was right at the end of this valley. It was channeling the pyroclastic flows, and then I concluded that there was nowhere. So helicopter came back in time. The really most violent eruptions are the Plinian and ultra-Plinian. And the explosive eruptions like Mont St. Helens in 1980 tend to form these steep-sided volcanoes that we call stratovolcanoes. Here's Mont St. Helens after the eruption, and this photo taken during the eruption. So I'm sure that some of you remember Mont St. Helens in 1980, very violent eruption, and it was predicted. Actually, people have evacuated. Some people didn't want to leave, so they stayed and died. But what volcanologists didn't predict well was the fact that it was going to have a lateral blast. We were expecting it to go up, so the hazard zone was actually smaller on one side than it really needed to be. But what's very interesting is that if you look at this painting by a painter called Paul Kane, this is in Canada, in Toronto, and Mont St. Helens had an eruption in 1874, and although I don't think he got things terribly accurate, it was a lateral eruption as well. So often by looking at history, you can actually learn what a volcano is likely to do. And but this painting had been, kind of forgotten, and although there was a bulge growing on the side, people really didn't figure out that there was going to be this massive lateral blast. So let's go on to the planets now that we know something about volcanoes on Earth. So first place where we see volcanoes is the moon. The moon has seas of lava. This is Mare Imbrium on the moon, and you can see some long lava flows here, hundreds of kilometers long. And the moon has basalts, but the composition is somewhat different. Lavas don't actually have water as volatile. And you have lava channels, some rather nice one. This is near where one of the Apollo missions landed. lava channels and collapsed lava tubes. And you don't see big volcanoes on the moon. You see some small cones, but mostly it's just these seas of lava. And what's telling you is that the lava was very fluid, and it just flowed almost like water. So on the moon, you find just these seas of lava. And even if you look at the moon with the naked eye, you see the dark areas. Those are the volcanic areas. So very interesting stuff. Actually, a lot of interesting research going on with recent data on the moon, and actually people finding more water than we thought existed there. On Mercury, there was a debate for quite a long time whether volcanoes on Mercury or not. The Mariner 10 mission saw some smooth areas, but we thought they might be from the impact of craters forming impact melt and smooth areas. But the Messenger mission actually has shown some volcanic features, such as this little guy here, I actually forget how many kilometers across it is, but this whole image here, and there's the volcano, this is about 270 kilometers across. And here for reference, for people who know Mercury well, that's the rim of the Caloris Basin. So now we know that volcanism has taken place on Mercury, and Messenger is identifying volcanic features. Venus, very interesting planet because it's got a lot of volcanoes. In fact, Venus has a lot of shield volcanoes, like this one here called Sif Mons. This picture is somewhat vertically exaggerated, but to show you the volcano, but it shows you the shape. So kind of similar to Mauna Loa in Hawaii. Again, very long flows. This is a radar image. Some collapse features, like this is a type of caldera or volcanic crater. It's called Serrava Patera. And some other strange features that we don't quite have on Earth that got nicknamed pancake domes. And these pancake domes are about 50 kilometers across. We think the pancake domes are actually formed by very viscous, sticky lava, but with little gas in the lava, so they just oozed out and spread out. And Venus has also very high atmospheric pressure, denser atmosphere than the Earth has, so that makes some differences in how the lava cools and how the lava behaves. But Venus has so many volcanoes and so many interesting volcanic fields. It's almost the greatest volcanologist paradise in the solar system, but not quite. Michael Caro painted this view of pancake domes on Venus. And, people might argue how accurate it is. Well, but it's useful, actually. It's very interesting to work with an artist because they want to visualize things, like what would it look like if you saw it from the ground, and most of us who, work with the scientific data just don't think about what would it look like, if you were there. But the artists do, so that's quite interesting. And another volcano that we put on the cover of our book, Mons, on Venus. And my favorite solar system volcano is the giant Olympus Mons on Mars. Now, Olympus Mons is the largest volcano we know of in the solar system, 600 kilometers in diameter and 26 kilometers high. So, Everest is really tiny compared with this. Only the volcano is so large in diameter that actually the slopes are very, very shallow, only a few degrees. So this is a shield volcano, again, similar to the ones in Hawaii. It has this long lava flows. And when I started working on Olympus Mons, we didn't dream of the kind of detail that we have now. We can trace all these lava flows from the Mars Global Survey, and now HiRISE, the camera on the Mars Reconnaissance Orbiter. The resolution is amazing. We're almost getting better resolution on Mars than we have on the Earth. But Olympus Mons has this tall scarp around it, and then some corrugated material all around it. And I'm not sure I have a picture of that. No, unfortunately I don't. But that corrugated material is what's called the Oriole material. So what I did for my first project was relate the existence of this scarp to the existence and extent of these large lobes of material on the skirts of the volcano, and I proposed that they were due to mass movement or landslides. And people actually at the time they thought it was a crazy idea, but eventually they actually accepted that, and we even proposed in our first paper that this mass wasting it could have been helped by volcanic activity melting permafrost. And I have had people later say to me, oh, well, that was really an interesting idea for the time. So sometimes you get lucky. Here is one of Michael Carroll's images of volcanic eruption triggering flash flooding, so causing ice to melt. And again, you can look at this as a bit of science fiction or fantasy, but it's interesting to try to visualize what these eruptions could have looked like on other planets. Now, the real volcanologist paradise is Io. Io is the most active body in the solar system. It's a small moon about the size of the Earth, but incredibly active. It's so active that we have lots of changes on the surface, and so I call it a volcanologist's paradise and a cartographer's worst nightmare, because you make a map and it changes. So the volcanoes on Io were discovered by the Voyager mission back in 1979, but the Galileo mission in the late 90s was the mission that really studied closely these volcanoes, and I was lucky enough to get hired by the Galileo mission to study Io. So why does Io have so many active volcanoes when other planets and other moons don't? Well, Io is in a very peculiar orbit. There's Jupiter. This is a montage, in fact, of Voyager pictures. There's Io, and then that's the closest moon, the closest large moon to Jupiter, and then Europa, Ganymede, and Callisto. These are known as the Galilean satellites because Galileo actually discovered them using his telescope just about 400 years ago. He first saw them on the night of January 7th, and then on the night of January 8th, he thought they were stars at first, and then the next night he noticed that they actually had moved. And I really like that because January 8th is my birthday, so I have this connection with Io there. But Io is, of course, about gravity, and Jupiter is massive, so Io is being pulled towards Jupiter, and it has this tidal bulge, like the moon causes tides on Earth, and only these are crustal tides. And if the other moons went there, Io would have this bulge facing Jupiter, would have a perfectly circular orbit around Jupiter, and there wouldn't be any volcanism at all, and it would be a very boring place. But because these other moons are there, they are also attracting this tidal bulge towards them, and they're distorting it, and that movement is what causes friction internally and causes the interior to be molten. So it's thanks to these other moons that Io has this volcanism, and actually the orbit is elliptical, not circular. So it's, and in fact, volcanism on Io was predicted about 2 weeks before the Voyager spacecraft got there. There was a paper published in Science in which some theoreticians actually had studied the orbit and predicted that the orbit of Io might cause it to have internal heating, and they said widespread volcanism might occur, which was a fantastic prediction. And about 2 weeks later, we used cameras on spacecraft for navigation, and the scientists had already found features that looked like volcanoes, but there was nothing that they could say was active. And a navigation engineer called Linda Morabito, young woman at JPL, was using the cameras for navigation, and she noticed these two strange things on, this is an overexposed, deliberately, image of fire, and because it was overexposed, you could actually see a plume over here. It's about 300 kilometers high, and it's the Pelee plume. And here on the terminator, you can see the top of another plume being lit by the sun. And so there were a lot of questions, and could this be another moon, unknown, coming behind Io? And well, eventually they nailed it, particularly when the spectrometer on Voyager actually detected sulfur dioxide and thermal emission over one of these locations. So this is a Voyager image, and this shows the Loki plume, about 100 kilometers high. And Io has these strange colors, yellows and reds and blacks. And it was immediately noted it had sulfur dioxide. These are colors of sulfur. And so Io has a lot of sulfur on its surface. And for a while, there was a debate, are these volcanoes erupting sulfur, or are they erupting, quote, normal lavas, like on the Earth, silicate lavas? And with Galileo, we established well that they are erupting silicate lavas, although the plumes have a lot of sulfur dioxide and there is a lot of sulfur on the surface. Well, this is Yellowstone. If Yellowstone was on Io, it would be, about 20 kilometers high. So you'd really have trouble taking a picture of it. And why the plumes so high? Well, it's not just because the gravity of Io is less, but it's also because Io has no atmosphere, so this material is erupting in a vacuum and it goes supersonic. And actually studying these plumes is very difficult because the modeling you have to do is actually quite hard. Io has lava lakes, lots of lava lakes. And this is, it looks like a psychedelic picture. And in fact, the first time I showed this to a colleague, he said, "Is this real?" This is a caldera called Tupan, so it's like a volcanic crater, and it's about 70 kilometers across. Now I'm going to explain what's happening here. On Io, everything that's black or very dark is either recent or active lava. We found very good correlation. And so this side is very active, and when we look with the spectrometer and get the thermal emission, we find this side is indeed very active. This side has active patches. So this is a cooled crust, but some lava is erupting through a cooled crust. And in the middle is an island that actually it's cold and it has frozen sulfur dioxide on top of it. And some of the Io calderas have these islands, and we haven't figured out what they are or how they were formed. But one way that we figured out that these were lava lakes is because when you look at the edges are actually hot. So the edges where it comes up against the island and also against the wall. If you look at the lava lake on Earth, we'll just first show you this image from Michael Caro of what the inside of Tupan may look like. But if you look at the lava lake on Earth, like here is lava, what we call it pond, because it's not very big, and it's no longer active. It was on Kilauea. You find lava cools very quickly when it gets to the surface. So you find this cool crust on top, but you tend to get these hot edges. And why? Well, if you think of like scum on a pond or on the bathtub, where it hits against the walls, it's where it breaks up. So on a lot of these craters on Io, these calderas, we actually find these hot edges, and that tells us that they're likely lava lakes. So that's part of the work that I did on Io. And actually this painting, which I'll go back to, was actually my first collaboration with Michael Carroll. He asked me, what should I paint on Io? You know, and I said, well, try painting Tupan. It's just this very beautiful and strange-looking caldera. So he painted the reds and greens we think are sulfur that actually melts down from the walls. We had lots of fun actually figuring out how steep these walls would be and how the jets of gas would actually go up and what it would all look like. And, you know, and in the end, I actually bought this painting. It's couldn't resist it. So these are lava lakes. This is another lava lake on Io called Loki, which is the largest caldera in the solar system. And this is an image of Loki. Again, you see lots of black, but an island. And, you know, how do these islands form? We're not sure. And this is an image what the interior of Loki might look like. We know that there are some cracks on this island, and with the spectrometer we can see there's some hot material on these cracks. And Loki, we think, is a type of lava lake. And so we left Io at the end of the Galileo mission. Our last data came in 2001, but 2007, the New Horizons spacecraft, which is on its way to Jupiter, its way to Pluto, actually used Jupiter as a gravity assist. So we got some nice data of the Jupiter system, including some nice images of Io. This is Io showing a plume up in the north called Chvastar and another plume called Prometheus. We were able to observe some changes. And this is a nice picture of Io and Europa. Now, you might know that the next NASA mission, next big mission to the outer solar system is going to Europa. And a colleague of mine sent this picture around to the team, and he said, now, if you had to choose which one of these bodies to send a new mission to, you know, which one would you choose? Just as a joke for the NASA people here. But Europa is also a really interesting place because Europa has a different kind of volcanism that we call cryovolcanism or ice volcanism. And Galileo actually showed us a lot of things about Europa we didn't know about. It's a very young surface, again, like Io, lot of cracks, and we think that there is a liquid ocean underneath this icy crust, and the ice crust has cracked, and the material has oozed out. And we know that there is heat on Europa because the tidal heating that affects Io affects Europa in some form. Well, you have heat, you have water, that kind of raises the possibility for some kind of life. So that's one of the reasons that Europa was it's so interesting to us. And what the interior may look like, well, there are people who argue about whether the crust is very thin. You know, most scientists these days go more towards this model, but maybe we have volcanoes underneath, and these volcanic materials coming up, and you know, and eventually finding its way to the surface. But there is a layer of liquid water, and one of the things that the next mission is going to find out is actually how thick this ice layer is. So we're going to have some answers there. And this is a region of very disrupted on Europa called Connemara chaos. It's a small region. It's about 70 kilometers across, and that shows how the crust has broken up and fractured, and got very fractured. Europa is a very exciting place to go to, and next mission, I hope we'll get there before I retire. But at the moment, I'm working on the Cassini mission, and Cassini did show some active cryovolcanism on this small moon called Enceladus. No, it's not really going to hit the Earth, but this gives you an idea of the size. So it's very small, but it's actually active. It has some plumes. And we actually suspected, because there were some very regions devoid of impact craters, we suspected that the surface was very young. But what Cassini found, there are these cracks near the South Pole, and we found that these cracks are warmer. These temperatures, by the way, are in Kelvin. But in 2005, we found that this that we nicknamed tiger stripes are actually warm, and that plumes were coming out of them. And since then, we have been observing Enceladus, plumes, these jets of water vapor mostly coming out. And here is an enhanced view showing you the extent of the plumes. This is a recent image from the end of last year. And we have seen that some of these jets have actually changed over time. They become, less strong, or new jets might appear. So we're monitoring Enceladus with Cassini to try to figure out what these plumes, really are, what they're made of, how deep down they're coming from. Because it's another interesting place. You have a liquid layer of water in the interior, and you have these jets of water vapor. So, maybe another place where there is a possibility of life starting. This is just a nice picture that Mike did of jets on Enceladus. And the moon that I'm really studying now is Titan. Titan, called it Saturn's mysterious moon, is Saturn's largest moon. It's the second largest moon in the solar system. And the Voyager spacecraft didn't see the surface because it has a very dense atmosphere, and Voyager didn't have the right, let's say, equipment, instruments to really penetrate this haze. And we have a radar on Cassini, and so with radar we can really see the geology of the surface. And some of us think that there is, at least that there was cryovolcanism on Titan, that there are features that are cryovolcanic. Not everyone agrees with this interpretation. We have a region here, for example, where you have some lobate flows, and several other regions on Titan where you actually see features interpreted as cryovolcanic by the majority, but not all, of planetary geologists. And an interesting thing happened when the radar found these lobate features that look like flows. And bear in mind that radar images are kind of harder to interpret than visual images. So you may not be seeing so much what's going on here, but the next slide should make it clearer. And then one of my colleagues working with the spectrometer actually had found, before we looked at this region, that there were some brightness variations, which he thought could mean active cryovolcanism. So there may be some degassing going on in this region. There is nothing that is actually really active like a flow. At the moment, we have not detected any thermal activity. So we don't think that these flows were actually active, but there could be some degassing going on. So it's interesting. And we got with radar 2 views of this region. And my colleague Randy Kirk at USGS was able to make this movie and which actually shows this flow. And you know, if you actually use this radar 3D, you can see it's about 200 meters thick. And so are these really cryovolcanic flows, or some people interpret them as fluvial deposits? Well, I'm on the side of cryovolcanism, but time will tell. And, you know, we have volcanic features elsewhere. For example, on Triton is one of the places where we find some smooth terrains and the pit chains where collapse has occurred, and some other features, and some plume streaks. So the outer solar system has cryovolcanism, ice volcanism, which is very different from magmatic volcanism, but we call it volcanism because it's a process that's bringing material from the interior to the surface. So you have to define also what the magma is for that body. And this is a little bit of, you know, science fantasy here, perhaps, but there is some science to it. It's this nitrogen ice melting and leaving strange shapes. Perhaps that's what we would see on Triton if we went there. And the future, well, when New Horizons will arrive at Pluto in 2015, this is the most detail we have to date of the surface of what's now the dwarf planet Pluto from the Hubble Space Telescope. And could there be cryovolcanic features there? I don't know, but it's going to be very interesting to find out. And it's going to be very exciting. In fact, when you look at the surface that you have never seen before, there are always surprises. There's always something really exciting going on. I still remember when we first got the Cassini radar images of surface of Titan, and it was only like 1% of the planet, but how exciting it was to actually see that real state for the first time. So we have a lot more to look forward to, and you know, they have a few books for sale, so I thought I would advertise them. But yeah, I need to put my son through college. That's all. But I'll be happy to entertain questions, and thank you very much.
I think we've got some time for a few questions for Rosaly, if people have got some. What's it? Oh, right here. Let me repeat it. She's asking about the pancake domes on Venus and Rosaly's impression about what they may be.
Yeah, well, I haven't studied them personally, and in fact, John can give his view as well if he likes. But what my colleagues who study Venus think is that they are made of very viscous lava, but that has very little gas. So the lava oozes out a bit like toothpaste. And we have some domes on Earth, like, for example, Lassen Peak. In California is a volcanic dome. That's what happened there. You know, lava just oozed out, only that it's not flat. And these domes, perhaps, you know, they oozed out very slowly and just flattened out. Do you have a different view? Of, okay. Yeah.
Over here. Why did such a large volcano form at Mars and not elsewhere in the solar system?
Well, probably several reasons, but one of them is the lack of plate tectonics. The Earth is the only planet where we have found plate tectonics. And so what happens to a place like Hawaii? The volcano starts building up, and then the plate moves, and the volcano stops building up, and the new volcano builds up somewhere else. Mars doesn't have plate tectonics, and we think it has a much thicker crust. So that enabled a big volcano to actually build up and be sustained. Though you're the Mars expert, you know.
I think he's right. Let's come back to this side of the room and start here first and then there. Let's see if I can summarize that. The role of water in volcanism is something stressed by you and by the movie beforehand. What happens to that water? How is it bound in the rocks, or does it go somewhere else?
Well, actually, these moons of the outer solar system, we think they actually have a layer of liquid water underneath an icy crust. And the composition of planets is different as you move out towards the outer solar system. And so the outer solar system has a lot of very icy bodies. And we think what's happening in those places is that you have a crust, instead of being made largely of rock, a lot of it is ice. And then you have a liquid layer of water, maybe water with ammonia or with nitrogen or some methane. You know, there are various explanations what the other things might be with that water, you know, and is so that layer would be like a let's say a layer of magma. That's why I said you have to define what the magma is for a body in order to call it volcanism. For example, if we have water, you know, coming up in a volcanic region like a geyser on Earth, we wouldn't call a geyser a volcano because water on Earth is not magma. But if something like a geyser is coming up on Enceladus, we call that volcanism because the material from the interior that's being brought up to the surface is water. And in fact, some colleagues and I had great fun actually writing a book chapter on redefining volcanism.
There's another question over here, yes.
Yeah, are there any indications that Olympus Mons or any other Martian volcano has been active in recent geological data?
Summarizing, is Olympus Mons active?
Well, we don't have any proof that it is active or that any volcano on Mars is active. You know, there are hints that perhaps, you know, Venus has some activity. You know, there's some methane on Mars that perhaps could be caused by volcanism. But the short answer is no. We might. I think it's not impossible that we could find some degassing, but we haven't found any yet.
Right here.
You know, the other large moons in the outer solar system that you didn't mention, is there any sign of volcanic activity of some kind on them, or is it possible that there is none?
On the moons that weren't mentioned, is there signs of volcanism there?
You know, like Callisto, for example, where it has a very old surface with a lot of craters, so there may have been cryovolcanic activity in the past, but nothing that we can recognize at the moment. So it doesn't mean that it never happened. It just means that we haven't identified features there. Indeed, you know, there's been some a few features of Ganymede that you know, people argue whether they are volcanic or not.
Just in the spirit of the fact that just half a century ago, there was a great controversy as to what the origin of the lunar features were, whether they were volcanic or meteoric. And in the interim, of course, we have very strange occurrences like the mist around Alphonsus and stuff. Is there any reality to that? Is there anyone still wondering if there's any active volcanism on the moon? And do you and your work relate back to some of those controversies that went on half a century ago?
Actually, oh, sorry, no. Okay. So he's asking about the lunar craters. There was a great controversy half a century ago. Were they volcanic? Were they impact? And then some of, I think you mean the transient lunar phenomena, so-called. Is there any evidence that there is? active volcanism on the moon. There were some observational things that I'm not sure anyone has quite explained what those transient lunar phenomena were, but there is no real evidence of active volcanism on the moon. Now, the controversy is very interesting because, yes, 50 years ago or even less, people thought many of these craters on the moon were volcanic, not impact. And in fact, my PhD advisor, who is retired now, came into the country business from volcanology because he was hired by someone who thought all the craters were were volcanic, and he wanted a volcanologist with experience on Earth volcanoes to prove it. And he started studying them and said, these don't look like volcanic craters at all. So, which I gather caused some disagreement. But it was actually the study of a crater on Earth, meteor crater in Arizona, that really sealed the deal. And Eugene Shoemaker, who was a very great geologist, unfortunately passed away, studied a meteor crater, in fact, for his PhD, if I'm not mistaken. And he showed that they were more similar to craters from nuclear explosions and, explosion craters than they were from volcanic craters. And in fact, when you really look at them, there are a lot of telltale signs. For example, impact craters are very round. You need a very glancing impact to form something that's not round. And that's because they are excavated by shock waves. Volcanic craters are collapsed and they're usually not very round. And then if you look at them in detail, there are a lot of things you can tell from the rocks. And the astronauts brought back rocks that actually showed that these rocks had suffered impact. So that pretty much sealed the deal. But I do remember in my graduate student days, there were still people who thought the craters were impact.
Okay, one last question right here in the middle.
What do you learn from the gas composition when you measure it? What does that tell you about the volcano, tell you about when it's going to erupt? What do you learn basically?
Okay, he's asking what you learn from the gas composition of volcanoes, and if you can use gas composition to figure out if a volcano is going to erupt on Earth. Yes, gas composition is one of the things that volcanologists look at. First of all, you can tell, a lot about magma chemistry, and there is a whole branch of volcanology which is actually looking at gases. And in particular volcanoes, if you get, most of the stuff, the gas that comes out of volcanoes is steam, is water. But in some volcanoes, if you get more sulfur dioxide or hydrogen sulfide, gases like that, it indicates that there is more magma actually moving towards the surface. So that can be an indicator that an eruption might happen. It's not the only indication, and we used particular seismometers to actually measure when magma is moving up.
Okay, please join me in thanking Rosaly one last time. And I'd also like to thank again our sponsors, Aerojet and NASA. And I look forward to seeing many of you here for the next installments of the 2010 Exploring Space Lectures. Thank you again, Rosaly. She will be available downstairs in the Milestones Gallery, and her books will be for sale out in the gallery. So please, if you're interested, stop on by.
Thank you.